Okay, to find the mean, what do we do? We add everything. Yeah, first we need to know that n equals 8. There are 8 numbers in the list. And yes, for the mean, we add them all up and divide by 8. If we add them all up, we get, what I believe, 136. And divided by 8 is at 17. So we got a mean of 17. Any questions on that before we move on? What's that? Oh, okay. That would do it, yes. Now for the median, what's the first thing we have to do? Put them in order. So 7, 12, 15, 15, 17, 20, 23, and 27. Just to make sure I've got them all there, I'm going to number them. And I do have 8. Also, numbering them helps us with the next step. Next step, of course, is to find the position of the median. How do I do that? Well, I can cross off the ends and find the center, or I can do 0.5 times n. Well, 0.5 times 8 is 4, which tells us it's between the 4th and 5th. Very good. So 4th number is 15, 5th number is 17. I add them together and divide by 2 to get 16. So I have a mean of 17, a median of 16. A mode of 15. Now I'm going to pause right there for a second and point something out. I'm going to draw this curve as symmetrical, but it really isn't. Our mode is at 15. Our median is at 16. And our mean is at 17. Remember we said if those are all equal or really close to equal, that this is symmetrical. It's a perfect bell-shaped curve. And while 15, 16, 17 is close to equal, it forms a very distinct pattern. It's the mean, then the median, or sorry, the mode, then the median slightly bigger, then the mean's bigger yet. And do you remember what direction we said that meant the data was skewed? Yes, it's stretched out to the right, like that. The direction that the mean is away from the others is the direction that it's skewed. So that means the right tail of this is stretched out. If we were to do a dot plot of this, let's put red dots on here. We've got 7, 12, 15, 15, 17, 20, 23, and 27. You can see just slightly more stretched out to the right end. Not a lot, though. Like we said, these 15, 16, and 17 are relatively close together, so it's not hugely skewed. Now, for this class, that's not something we're going to be tested on, but if you're looking at this type of information, that's the basics of really being able to break down a data set and think about what it looks like. Next, for the mid-range, how did you find the mid-range? We take the largest and the smallest, and we add them together, and we divide by 2. That does give us 17. Finally, the range. Largest minus the smallest gives us 20 for the range. The variance is going to take a wee bit more work. I tried to be nice to you here by giving you a mean that came out to a whole number of 17, which makes the variance and standard deviation a little bit less work. Step 1 is to find the mean. What is step 2? Yes, subtract the mean from each. So we've got, that was, we've got 7, 12, 15, 15, what do we have, 17, 20, 23, and 27. And we are going to subtract 17 from each. 7 minus 17. Negative 10. 12 minus 17. Negative 5. 15 minus 17. Negative 2, and I bet it's still negative 2 for the next one. 17 minus 17. 0. 20 minus 17. 3. 23 minus 17. Is 6, and 27 minus 17 is 10. Now at this point, if we wanted to double check to make sure we were going in the right direction, this is not part of the calculation at all. It's just a way to double check. These, remember, are called the deviations. The sum of the deviations should always equal 0. If I add those up, they do come out to 0. So that's a way to double check just to make sure that at that point you haven't screwed something up. Typically, the biggest mistake made at that point is that you calculated your mean wrong. So that's one place where you can catch that your mean is off. The only other way that can be off is if you subtracted at least one of them wrong. What is step 3? Not square root, square. Negative 10 squared, 100. Negative 5 squared is 25. Negative 2 squared is 4, and I bet it's 4 again. 0 squared, 0. 3 squared, 9. 6 squared. And positive 10 squared is also 100. What is our step 4? Find the sum. Sum of the squared deviations, which is 278. Looks right to me. What is step 5? Very good. And n here is 8. So n minus 1 is 7, which means we divide by 7, which is going to give us 39.71428571429, right? We'll stop there. 38.71, we'll call it. And of course, that is the variance. Now, the next thing we're supposed to find is the standard deviation. It's nice that we found the variance first, because now we do what? Now we square root, which gives us 6.30. That is our standard deviation. What that is telling us is that on average, those numbers are each 6.3 units away from the mean. Any questions? Oh, come on now. No, it does not. I'm gonna have to bite the bullet and do it the old-fashioned way. Yep. Oh well. So much for technology being my friend today. No, I've warned the text that, they should give me a bag to return this thing in. They didn't think that was funny at all. I told them I wasn't really trying to be funny. We'll see. So with this set of numbers already put in order for you, our next challenge is going to be to find the 70th percentile and the 35th percentile. And what percentile is the 23? And what percentile is 15? Find the first quartile and the third quartile. I'll give you guys a few minutes to work on those. 70th percentile. So we're going to find the position. So 70% would be 0.7 times 8 is 5.6. So that rounds up to the 6th spot. So that would be the 20. So the 70th percentile is 20. For the 35th percentile, 0.35 times 8 is 2.8, which is going to round up to the 3rd spot. So 15 is the 35th percentile. I'm going to stop there. Any questions on those first two, finding those percentiles? Now, next, we're going to go the other direction. What percentile is the 23? Well, in the list, how many numbers are smaller than 23? 6. So there's 6 smaller plus. Remember, it's 1/2 times the number that are equal. How many are equal to 23? Just 1. Okay. And that's going to be divided by n, which is 8. So this is 6.5 over 8, which is 8.125, right? Or 0.8125, I should say. 0.8125, which is the 81st percentile. Any questions on that one? Now for the 15, how many are smaller than the 15? 2 plus 1/2 times how many are equal to 15? 2, and then over n of 8. So 1/2 times 2 is 1. 2 plus 1 is 3. So that's 3 over 8, or 0.375, which will round that to the 38th percentile. If you left it as 37th, that would be fine too. How many of you guys had all 4 of the percentile questions right there so far? Cool. Don't have to sound so surprised. Uh-oh. Ruh-roh. We may have to take a look back at those then. First quartile and third quartile. Remember, the first quartile is just the 25th percentile. So that's going to be 0.25 times 8, which is 2. But since that's a 2, that means it's between the second and third. So that means it's going to be 12 plus 15 divided by 2, or 13.5. And finally, the third quartile, 0.75 times 8 is 6. So it is going to be between 6th and 7th. So it's between 20 and 23. So 21.5. Can anybody tell me why I didn't ask for the second quartile? Yeah, the second quartile is just the median, and we already found that of 16. So now with these numbers, the other things I could have asked for would have been max and min. What's the max? 27, and the min? 7. And we did talk briefly about this box plot. And this box plot really is an important plot. And we've got the min of 7, so I'm going to put a dot at 7. First quartile of 13.5, so I'm actually going to put a line at 13.5. Median was 16, I put a line there. Third quartile, 21.5. And then the max at 27. I connect the box between the first and third quartile, connect the minimum and the maximum, and that shows me where it's spread out. I can see the data is fairly tight together right here, but the other 3 spots are almost equally spread out because they're almost the same size. Remember, each of those pieces is 1/4 of the data. Now I want to mention something. It's another measure of spread. And it's something we briefly mentioned the other day. It's called the interquartile range. And that'll be the last time you ever see me write that whole phrase out, because I'll refer to it as the IQR. What the interquartile range is the difference of the third quartile minus the first quartile. So for this data set, that's 21.5 minus 13.5, which is an interquartile range of 8. Now this next piece would never appear on one of our quizzes or tests in this course. I bring it up because any of you that were to go on to a 4-year degree somewhere, one of the courses you would have to take would be a full-blown statistics course. And this would be one of the basic things in about week 2 or 3 of a full statistics course, would be finding outliers. So outliers, remember we said, are unusual values. They lie way out away from the other values. And one of the ways of judging an outlier is by using the interquartile range. We call them the fences or limits. So we're going to find a lower limit and an upper limit for our outliers. To do that, we're going to take 1.5 times our interquartile range. 1.5 is a constant. So for this data set, that's 1.5 times our interquartile range is 8, so that gives us 12. The lower limit is your first quartile minus the 1.5 IQR. So our quartile 1 is 13.5 here, minus 12 is 1.5. So what that means is anything smaller than 1.5 would be an outlier. Well, our smallest number here was 7, so there are no outliers on the lower end. For the upper limit, we take the third quartile and we add the 1.5 IQR. So our third quartile is the 21.5. We add 12 to that, we get 33.5. 33.5 is the upper limit. Anything larger than that would be an outlier. Well, here our largest number is 27. So there are no upper end outliers either. So this data set had no outliers. If there had been an outlier, what would have happened is when they made the box plot, it wouldn't have changed the center of the plot at all. And let's just say there was an outlier on the upper end. They would have cut off that whisker, and then just put an X up there. If you see a box plot that looks like that, this X up here is a data point. It's just an outlier. So they cut off the box plot at the point below that. Or maybe there's more than one outlier at the point that's below, the last point that's below this upper limit. We didn't have any outliers. Again, this is not something you'll be quizzed or tested on for this course, but it's something as you analyze, if you look at these, you know what that means. Let's talk a little bit more about the mean and standard deviation and what they're used for. Remember, we said if the data is normally distributed, or at least really close to it, that the mean is approximately equal to the median. The reason I bring that back up is what we're about to do technically uses the median. But since the mean and median are the same, if the values are good, we're going to use the mean. Pretend that looks like a symmetrical bell curve. That's not even close. Let me try that one more time. I'm not saying that's any closer, but it'll work. The center of this curve, and of course the mean equals the median, which should also be approximately equal to the mode as well. The center of this curve, the highest point of the curve, should be the mode, which should equal the median, which should be approximately equal to the mean. Another way of defining an outlier is more than 3 standard deviations above or below the median or mean. So we're using the mean in the middle of this curve, but it could just as well be the median. So what do we mean by 3 standard deviations? Well, we go out in steps. Here's 1 standard deviation. I'm going to mark that as -1 standard deviation. That's 1 standard deviation below the mean. I can go again. That'd be -2 standard deviations. That's another standard deviation below this value here that I had the 1 standard deviation at. Then I can go down another step. That would be now -3 standard deviations. Anything below this value here would be an outlier. And I can go the other direction. I can go +1 standard deviation. I can go another one, so I'm at +2 standard deviations. And another one, so I'm at +3 standard deviations. Anything above that value would be considered an outlier. Why are they considered outliers? Well, because less than 0.15% of the data will be less than 3 standard deviations below the mean. And less than 0.15% of the data will be larger than 3 standard deviations away from the mean, above the mean. In fact, there are definite percents for each of these steps. Between the mean and 1 standard deviation away, 34% of the data is between the mean and 1 standard deviation below. 34% of the data is between the mean and 1 standard deviation above. 13.5% of the data is between 1 and 2 standard deviations below the mean. 13.5% of the data is between 1 and 2 standard deviations above the mean. (2.35% is between 2 and 3 standard deviations away from the mean on each end. So what that really comes down to is within 1 standard deviation of the mean is 68% of the data. Within 2 standard deviations of the mean is 95% of the data. And within 3 standard deviations of the mean is 99.7. 99.7 is 997 out of 1,000. That means only about 3 out of every 1,000 data points will be more than 3 standard deviations away from the mean. That's why we call them outliers. 3 out of 1,000 is pretty unusual. Right now, I'm guessing this curve doesn't make a lot of sense. So I'm going to put some numbers in it. What I have given you, these percents are constant. Those are the same no matter what. I'm going to take these out because those can be confusing. If I hit the 8, there we go. And so we're just going to talk about those ones that are there right now. Let's say that I look back at the 13 years or so that we've taught this course, and I say that the mean final grade in this course is an 84. With a standard deviation of 8. What does that mean? But what that means is at the center of this curve down here, the mean is 84. As I move to the left, I subtract the standard deviation. Standard deviation is 8. So what is 84 minus 8? 76, right? What's 76 minus 8? 68. And 68 minus 8 is 60. Going to the right, I'm back to the 84 at the mean again. What's 84 plus 8? 92. What's 92 plus 8? 100. And then 100 plus 8? 108. Now a C minus is actually a 77, but we're going to say it's a 76. I'm going to ask what percent of students would you expect to score above a 76? Well, 76 is right here. Above is in this direction. So if I add those percents all together, that would be the percent I would expect to be above 76. If I add those all up, I get 84%. So what that's saying is 84%, that 8 needs to stay, receive a C or better in the course. Now, technically, you have to have a C, not a C minus. So it's actually 80%, not 84, or not 76, but still, you get the picture. Now, 93 and above is an A. So let's say I ask what percent of students score below a 92. I'll get rid of this. Here's 92, and I add those all up, right? That's below 92, right? Adding those up is 84%. Let's say I ask above 100. I've had a few students through the years that have had more than the total number of points possible at the end of the semester. They did all the extra credit and got them right. Well, here's 100. I add those up, I get 2.5%. Or I might get less than 76. Well, here's 76. If I add those up, I get 16%. Or I might ask between 76 and 100. Well, here's 76. Here's 100. If I add those up, I get 34 plus 34 is 68, plus 13.5 is 81.5%. Does that make sense? Now, those percents are a constant. So I'm going to pause. If you don't have that bell curve down with those percents underneath it, now these numbers here, the 60, 68, 76, 84, 92, 100, 108, those numbers change. The percents do not. Those percents correspond with the mean in the center, and subtracting a standard deviation every step and adding a standard deviation every step. But I'm going to give you a minute to get those percents down in your notes. Anybody need more time to write them down? Realistically, as long as you have half of it down, the rest you can fill in later, because it is symmetrical. So let's see if we can apply this to something. So you want to buy a house. You do your research. First of all, you got to decide what you want for a house. You decide you want 3-bedroom, 2-bathroom. And you do your research. You look up in the area that you want to buy. Let's say around here, the mean selling price. And I do mean selling price, not asking price, because those can be very different. There are houses that can ask for 140,000 and sell for 99,000. So what they actually sell for is what is paid for them. In this area, for a 3-bedroom, 2-bathroom house, the mean selling price is about 112,000. With a standard deviation of about 18,000. So what does that mean? Well, we're going to draw our curve here. Pretend that's symmetrical. And remember, these percents here are constant. They do not change. What number is going to go underneath the center right here? 112. And I'm just going to write the 112 and leave the 3 zeros off. We all know it's 112,000, right? As we go to the left, what number goes here? 94. Where'd that come from? Yes, 112 minus 18. What goes here? 76. 94 minus another 18. And what goes here? 58,000. Any questions, first of all, on where these numbers came from that we just put in there? Okay, next, any questions on where these percents came from so far? Those percents are just constant. That's the percents that are always in the curve. Now going up to the right above the mean, what's this next number going to be? 130. Yep. The 112 minus, or 112 plus 18. This one's going to be 148, and this one, 166. And let's say you find a house, the price on it is $148,000. And your real estate agent is telling you, you better put in an offer on this house right now. It's not going to be around very long. You better put in an offer now before somebody else buys it. And yes, it's a nice house. Has a lot of things that you don't necessarily need, but you like them. But here's your argument, or here's the numbers behind it. Here's 148,000 right there. There are two ways of looking at this. If I add together those 2%, I can say only 2.5% of 3-bedroom, 2-bathroom houses in that area have sold for more than 148,000. So that's telling us is that this house is kind of expensive. The other way we could look at it, we're looking down here. If I added those up, that's 97.5% are cheaper than that house. 97.5% of houses in that area that are 3-bedroom, 2-bath will sell for less than 148,000, which means there's probably a pretty good chance you're going to find another one that's 3-bedroom, 2-bath that you like that's less money. Does that make sense? Okay. For a job with mean wage of $14.70 per hour with a standard deviation of $1.60 per hour. What percent of employees earn less than $13.10 an hour? More than $17.90 per hour. Between $13.10 and $16.30 per hour. And between $11.50 and 1630 per hour. I'm going to give you a minute to, let's draw our curve here. Put in our percents. What numbers go along the bottom down here? Well, 1470 will go in the middle. Now going left, it would be 1310, 1150, and 990. Okay. Going the other way. 1630, 1790, and 1950. So for the first one, less than 1310. That'd be those numbers. That adds up to 16%. More than 1790 is right here. Those add up to 2.5%. Between 1310 and 1630 is between here and here. Those add up to 68. And 1550 and 1630 would be 81.5%. Any questions? Now that's a very quick way of analyzing data and drawing some conclusion from it. Like you saw that buying a house thing. It's a great way to see if what you're doing is in line with reality. It's very easy to jump to conclusions if you just use a mean. For example, let's say you're buying something and the mean price is $63. And the one you find has an asking price of $79. That's a $16 difference. That might look like a big difference. But what you need to know is the standard deviation. If that standard deviation is $24, well, now if you're looking at the curve, this is 63. The next step up is 87. Your $79 is somewhere in here. So the percent that's more than $79 is going to be more than 16%. This is, since the curve is symmetrical, we don't need to fill this in. This half here is 50%, right? That from here to here is 34%. Well, 79 is somewhere in the middle of that. We don't know exactly where in the middle, but somewhere in the middle. So we know that this would from here out would be 16. There's more than 16% that's larger than that, less than 84% that's smaller than it. So even though that $79 is well above the 63, it may not be way out there. You know what I mean? This example I did here, I purposely did not put the $79 at a standard deviation. That's one of the weaknesses of using this. This is what we call the empirical rule, by the way. And the empirical rule states those percents that we had put in here before. That's one of the weaknesses of the empirical rule is if the number you're looking for is between those standard deviation steps, it's difficult to determine what the percent is. This is a good time to take our break, but when we come back from break, we're going to talk about some methods that help us determine if we are between those standard deviations. So let's take our break. It's about 10, it'll be 10:13 here in a couple.